Hello, I'm Graham Horton and welcome to today's video. A little bit of a different video today rather than a tutorial or a product review. I've got a how-to, and I've got a how-to how to convert a wall clock that's used indoors so you can use it outdoors, but the knack is here we're going to use solar power to power the clock. The reason being, I've got a couple of garden clocks out there, and as the alkaline battery starts to deplete, the clock starts to run slowly, and it's done that over a period of time. So when you're outside and looking for the time, you can end up being 20 or 30 minutes behind the schedule. So I thought, why can't I power this from solar power, and have done with changing batteries? So last June I did a prototype unit, and it's been out in the garden since last June. Been through the summer, been through the winter up to now, and there's been no issues with it. So I thought I'd just show you how I built one of those clocks in case you wanted to try one yourself. So it's a standard indoor wall clock, a 12-inch wall clock with a standard clock movement in there, powered by a 1.5 volt alkaline battery. The fact that we're going to power this from a solar cell, which is a 30 by 30 millimeter solar cell, rated at something like 1.5 volts, will charge up the nickel metal hydride battery that we're going to use in the clock to a sufficient level each day to maintain the clock even for several weeks if there's no sunlight. Now, the fact that we're using a solar cell to charge that nickel metal hydride battery, I'm using something like a 200 milliamp hour battery, so in full sunlight it doesn't take very long to charge this. The charge current I've measured is around 50 milliamps. In the dark, I haven't got a diode in circuit with here. I could use a Schottky diode or a germanium diode to prevent back current flow, but over the period of time I've been testing this since last June, I haven't had any issues with the clock stopping because it's run out of charge. The reverse current is something like 3 milliamps, so it's not a great deal of drain, and that's easily topped up the next day. So no diode, nothing else in the circuit except the solar cell in parallel with the nickel metal hydride battery. So we're going to first of all have a look how you get into the clock, and then we'll modify it to take a solar cell and then the nickel metal hydride battery to power the device. I'm going to use very simple tools. We'll need a soldering iron, we'll need a drill with a suitable hole cutter to cut a hole for the size of solar cell we're using. I've used one of these stepped cone devices, but you could use an ordinary hole saw. For the 30 millimeter square cell, we could use a 28 millimeter hole saw. Now, you can get these cells from Amazon. I'll put a link to them in the video description below. But cheaper than that, if you go to your dollar store, pound store, they normally have these little lights on sale. This one was actually just £1. It's got a 25 millimeter solar cell in there, which will be sufficient as well, again for a 200 milliamp hour battery. Just need to cut around there and take this out of the circuit, and you've got a very usable cell. So I'm going to start by first of all removing this movement from the clock. Now, this type of clock, they're all slightly different, is held in place with tabs all around the outside of the periphery. So we're going to undo that and lift the module out. That means I can drill in here without any of the swarf from the plastic getting into the mechanism. So the first thing I'm going to do is to remove the battery. So we'll remove the battery. It's an alkaline battery, but we won't be using that. We'll be using a nickel metal hydride battery, which is designed for these outdoor solar projects. So this one is a 200 milliamp hour. But I've also got one which is 400 milliamp hour, and this larger one which is a 700 milliamp hour. But I found if you use the 200 milliamp hour or 300 milliamp hour, if that's a standard, you get a good balance between the point of time when there is no sun and the clock is running on the power that's been stored in the battery, to being able to charge up to the 1.2 volts when the sunlight reappears. So I found 200 milliamp hours is the sweet spot for this type of application. So that's the one we're using in this project. So we're going to remove this clock from the frame, and I found that if you take a screwdriver or a tool like this and we insert that between the case and the clock, and then just go around the outside, just gently prying away to remove the module from the device. So every time you get to a tab, you just need to pull that back slightly, and it allows you to free up the movement. If you find the tabs are slipping back, you can always put a piece of paper in there or something like a cable tie just to stop it from flipping back. But you can generally just work around the outside edge of this type of clock anyway and release those tabs. I'll just put the front of the case with the glass on one side for a moment. And you can see we've got the movement here. What I intend to do is to put the solar cell at the bottom of the device so that the wiring is shorter to the battery terminals. You could put it at the top and bring the wires down, but I find if I put it at the bottom there, then I can get the wiring to that place very nicely. You need to just move the hands out of the way of the position where we'll be drilling. We want to make sure that we keep clear of the numeral here, but on this particular clock there is a wall hanger, so this is the wall hanger which appears there. So I've only got that amount of space to put the solar cell, and if we look at that, it is very close to the limit of what I can achieve with this clock. So the position will have to be quite precise. So I'm just going to mark the bottom and the top with a pencil so I can find the center point so I can drill that. So something like that should give me the position. So this is a 30mm cell, so I need a hole saw which will cut me a hole just slightly less than 30mm. Now for that purpose I've got one of these cone-shaped drill attachments. You could use a standard hole saw if you've got one which is around about 28mm, but this is in steps, and we go from 6mm to 28mm, 30mm. So we're going to go to the 28mm step, and that should give me enough room to put the cell in there and have some support for it. So what I'm going to do first of all, although this has got a pilot on it, I'm going to drill my own pilot hole with a small drill, and we're just going to drill in there to give me that pilot hole position. So that gives me the pilot, and now we're going to drill from the face of the clock so we don't get a burr. And actually that doesn't look to be in the center. That's surprising because I thought we'd marked down the center line. So I'm just going to adjust that. Obviously because this is going to be cut out, it won't make any difference. So we want to be roughly there for our center point. So we'll re-drill that center hole from that point there. Now I'm going to raise this up slightly so we can get the rest of the drill down there without it drilling into the tabletop. So I'm just going to find a box to do that. So I've just supported the clock on a box, and I'm now going to drill down here, and I'm going to go down to the 28mm position. So the 28mm is the third ring down, so that is where we're at now. We'll just check the solar cell underneath there is just a nice fit. So these solar cells, as they're provided from Amazon, do have a protective film on the front, so we'll remove that first of all. And this is going to fit so that it is over the centre of that hole. Now the positive for the clock movement is here on the left hand side, so I'm just going to orientate that cell round so that the plus is to the left and the minus is to the right. So we're going to just fit this in place. Just got a slight burr there, let's just take that off. There we go. So the cell sits nice and flat, and I'm just going to use a little bit of hot glue to hold that in position. So with a hot melt gun, and we're centered over the hole, we'll just add a little bit of glue to hold that in place. And same on the other side. We'll just check the position. We'll just move it slightly up to get rid of that marking of the wiring, so that is in the right position. And now we'll finally just add some more glue to the bottom and a little blob on the top, just to hold everything in place. So now we're going to wire from the solar cell to the clock module. Now I've tried to solder onto these on previous attempts, and unfortunately some of these tabs tend to be steel or tin plated iron or something like that, but they don't tend to solder very well. So I found that if you just push the wire down the side here, it's enough to hold it, and the battery is going to spring those tightly against the wire, so there should be no issue with the connection. So what we're going to do now is to solder our wire from the solar cell to the battery. So I've got two pieces of wire which I've prepared, and I've put on here some ferrule so that they will stick nicely down there, but if you tin the wire you'll have the same effect. So I'm just going to use my old faithful big soldering iron here to help me solder these on, but an ordinary 25-watt iron will do the job. This is a Weller Expert. It must be 20 years old or more. Had this for a long time. In fact, it might be even more than 20 years old. So we're just going to tin the two tabs on the back of the solar cell like so, and I'll also tin the two wires that are going to attach to there. So here's the first one, which is the positive. And the negative one. So they're tinned. Now I'm just going to solder these to the solar cell. So here's the negative one. And the positive terminal. And then we'll now just go up to the battery box. But to add a little bit of support, I'm going to add some hot melt glue to the back, and it also helps to tropicalize the connection to the cell so it won't corrode at that point. So we'll just add a little bit of hot glue there, and also on the terminals that come through from the solar cell. So now I'm just going to push this down by the side of the movement. So that goes down between the movement and the plastic case, like so. Probably better there. And the same with the positive side. You might need just a screwdriver or something just to pull out the tab and then get your wire down by the side of it, like so. And then when we put the battery in there, that will tighten up that connection. But again, to add some stability, we're just going to add a little bit of hot melt glue to hold those wires in place. I'm just going to switch on a small spot lamp here. So you can see with just the light from a little spotlight shining on the clock, you can see that the movement is actually going round with the power of a small spotlight. But the sunlight is more intense than this. In fact, this is only sort of just over 600 lux at the moment, where the sunlight can be up to 100,000 lux. So we've got enough power from that cell to provide power for the clock movement. Well, the last thing to do now is to reinsert that movement into the clock body, and then make sure that the tabs are securely fastened to help with the prevention of water getting into the device. So here we have the front face of the clock. Just blow that bit of swarf off there, and it's a case of just assembling this into the clock front face, aligning the tabs in the outside edge with the tabs on the front of the case. Snap them all down. And we have our completed clock. We have our completed clock, and we'll set the time to, what was that, 2 minutes to 3. So that's it for the video. I hope you found it useful, and of course if you're new here and you're liking this already, why not hit the subscribe button and the bell notification icon, and you'll be advised when I upload new videos to the channel. Coming up shortly will be another construction program for you, and it's going to be a light meter which will measure incident light. You can use this for just measuring lux values, or you can actually use it for photographic exposure, which I'll have converted this unit for. Uses a standard BH1750 sensor, which is ideally suited because the spectral response is exactly the same as our own eyes, so it's great for exposure calculation. I'm using the Arduino ESP8266 microprocessor, which has an onboard OLED screen, which keeps this very simple and combined. So I'll show you the code that I've developed for it and show you how it can be used to calculate exposure. And behind that I've got another build project, and it's going to be a colour temperature meter. So this again uses a dedicated cell which will measure colour temperature in degrees Kelvin, so you can actually measure your light temperature and then be able to set your camera to the correct operating temperature. So that will be going up in a couple of weeks' time. So until then, thanks again for watching. Please do take care, and I hope to see you all very, very soon. Goodbye for now.